Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, the speaker today is Alec Agarwal. He was a student of Peter Bartlett and Martin Wainwright, and he's going to be talking about some computational trade-offs in statistics.
Okay, so the talk's going to be kind of at the intersection of some statistical and computational issues, and particularly we're going to try to understand what happens when we try to take computational issues into consideration jointly with the statistical complexity of the final solution that's being computed, and the results will involve joint work with my advisors Peter and Martin along with other collaborators at Berkeley. So let me begin by briefly motivating why we might need such a joint study of statistics and computation, and start with an example that I was working on at Yahoo Research this summer. So the problem we were looking at is how to display an ad given a web page, and the criterion we want to optimize is the probability of a click by a user. And we formulate this as a classification problem where given a pair of an ad and web page, we are trying to predict whether it will attract a click or not. And we can do this because we have the past click logs which we try to use to learn a good classifier on the future data. Of course, the problem is that these logs are growing in real time, so you can't really think of having a small subset of examples that we are dealing with. We of course do subsample the big logs for computational purposes, but despite the subsampling, we were dealing with as big as 17 billion examples, and the reason you actually need that much data is because the model being estimated is not small either. In particular, we formulated it as logistic regression, and our parameter had something like 16 million dimensions, so we really did need a fairly large amount of data. However, so it might be very easy to think that this is a purely computational issue at this point, and we just got to come up with an efficient algorithm to solve this problem. And at some level, one of the cases I will make today is that's not entirely true, and this will become more clear in the second example I'm going to talk about today, which pertains to what's being called the Netflix challenge, where we want to predict ratings that users would assign to movies, and we get to see a certain subsample of these ratings. So in particular, the data set that Netflix made available had something like 100,000 examples, and the number of parameters in this case was staggeringly large, much larger than the number of samples. So people have attempted a lot of different ways to approach this problem, and one particular class of solutions that people have attempted have been based on convex optimization problems. And what we'll show is that these convex optimization relaxations that people have looked at, so now you have to solve that relaxation, and if you think of sort of the worst case complexity of known algorithms to solve these relaxations, then we can do much better than that worst case complexity. If we take the statistical structure of this problem into account, we will get a much better result, and we'll see the details of this. So kind of the case I want to make at some level is that we, rather than viewing the sort of statistical or computational complexity of these problems in isolation, what we want to really do is try to understand the joint behavior of these two phenomena. And sort of a very conceptual cartoon that I want you to have in mind is, so we'll first start from a simpler picture, not taking this into account, which is often what a statistician would have in mind, where they're trying to infer a parameter theta star. We can think of this as a p-dimensional parameter. We get certain data we get n data samples to infer this parameter, and for instance in the click prediction example, each sample would consist of ad web page pair. You observe 0, 1 valued labels whether it got a click or not, and you've got features encoding the ad web page pair, and then you infer a parameter theta hat from this data and you try to ask the statistical risk of theta hat, and maybe as a function of n and p typically, for instance. What I propose is to augment the picture a little and actually think of what's going on computationally as well inside. And
what is the risk of an estimate?
So the risk can be, for instance, something like the distance between theta hat and theta star in L2 or in some other metric, or it could be some other loss function that you compute and use to estimate the quality of theta hat. And so the picture that we would bear in mind today is to take the computation into account as well and think about what we do with the data. That the data goes into a black box here. I'm not going to describe the workings of this black box right away for now, but whatever this black box does, we get b units of computational time. Again, for now we'll keep this at an abstract level, and we would like to understand the risk of theta hat not just as a function of number of samples and number of parameters, but also as a function of the computational time now. And the reason why this is interesting is if we understand this quantity, then we can try to answer how the statistical and computational aspects interact with each other and how we can trade one off for the other, rather than just having a separate understanding of the two quantities. Now the biggest missing piece from this picture, of course, is a specification of this computational black box, and I haven't done that because that's kind of the hardest part when trying to attack this problem. So what I'll do in the talk is I'll go over a series of examples. In each example there's going to be an associated notion of this computational black box and computational budget, and we'll try to answer questions such as this in that framework. Okay, so the first example we're going to look at is to try and understand the fundamental computational complexity for a class of for a certain class of estimation problems. And the notion of computational complexity here is going to be in terms of queries to a certain noisy gradient oracle, and within that framework I will present certain minimax results for computational complexity of some convex estimation problems and some sparse estimation problems, and we'll see more details. The second aspect of the talk is going to be about computation of high dimensional estimators. So I'll start by describing some computational challenges that we face in high dimensions, but how we can avoid these challenges if we look at the statistical structure of the problem, and these results will have implications for problems such as sparse linear regression and low rank matrix completion, low rank matrix completion being sort of the Netflix example we saw in the beginning. And very briefly I will, if time remains, I will talk about how we might generalize these ideas if we want to solve these problems in a distributed fashion rather than solving them all on one computer then. Okay, so starting with the first example, M estimators are a fairly broad class of estimators that people look at in statistical literature, and the very nice aspect of them computationally is that they can be thought of as solutions of optimization problems. So typically these estimators are expressed as minimizing a certain loss over the data under some parameter space, and consists of many common examples such as maximum likelihood estimation, where this loss will be just the negative log likelihood, or least squares regression, logistic regression, and so on. And statistically these estimators are pretty well understood. So what's for instance known is that under mild conditions this theta hat would converge to a population parameter theta star that minimizes the expectation of the same loss function, right? So again the thing I want to point out here is that theta star again is expressed as a solution of an optimization problem, although in this case the optimization problem is not fully specified because we do not know this distribution, otherwise the statistical problem would be trivial.
I see. So by definition then the risk is the expectation of this?
For this part of the talk, yes, exactly. Now in order for computational tractability we are going to make certain assumptions first. So we are going to assume that the loss function is convex in the parameter theta, and we are going to assume that the parameter space omega is convex, which a lot of interesting examples would satisfy. And the upshot of these two assumptions is that we can think of both theta hat and theta star as being solutions of convex optimization problems, and that's from a computational standpoint that's naturally relevant because there are lots of algorithms available for solving convex optimization problems. and in particular a class of algorithms that has been very effective for solving large scale problems is the stochastic optimization framework, and I'll talk a bit more about this framework over the next couple of slides. But the question we will try to ask today first is, what is the minimal computational complexity of the best possible stochastic optimization algorithm to solve problems such as computation of theta hat or theta star? So note that what we want is a lower bound on the complexity of the best possible algorithm. We are not going to just do this reasoning by taking handful of algorithms and maybe reasoning about their complexities. Yeah.
Why would we talk about the complexity of computing theta star?
Because theta star is the thing you eventually want to compete with, right? So.
But we would never be able to compute it because we don't actually have access to the distribution.
So you don't have access to the distribution, and hence you cannot compute quantities such as the value of the risk or the gradient of the risk, but you can compute stochastic estimates, right, just by drawing a sample. And so which is why the stochastic optimization framework kind of applies both to theta hat and theta star computation. Yeah. Okay, so now again, I told you most things except the most important thing, which is what's the notion of computational complexity here. And because we are in a convex optimization framework, we are going to use the notions of complexity that people in convex optimization framework have found to be very useful. So we'll look at the notion of oracle or black box model of complexity that was proposed in the work of Nemirovsky and Yudin from 1983. So the idea in this work is that there is a certain class of functions that we have. And one way to think about this in the statistical setting that we are talking about is, if you look at this problem, let's ignore everything else. There is a certain loss function, and then there is a distribution inducing the expectation. And by varying this distribution, you can get many different risk functions. And of course, we don't want an algorithm that just works for one distribution. We want an algorithm that works for many distributions. So by looking at the class of all risk functions that are induced by taking different probability distributions, we can get a function class such as this.
So the class maps an estimator. For every distribution, you have the function that maps an estimator into the expectation of the loss and of this estimator under this distribution? Yeah,
exactly. So the functions will be exactly these expected loss functions.
And L is fixed.
L is fixed for now. I mean, you can vary both L and distribution. I'm just for simplicity talking about keeping it fixed.
So these pictures are different thetas and different distributions.
So we are thinking of this as a function of theta, really, right? This is the risk.
It's of a z, and it's a function of theta.
Exactly, it's a function of theta. So really, the thing on the x-axis here is theta, right?
So I mean, when I think of a concrete problem, will L have some free parameters in it or not?
Yes, it could, and those would. So for instance, you could just think of. So you could think of L of theta here as being something like absolute value of theta minus z, but you could have a scalar such as a constant times that, and that will give you scaled versions of the same quantity. Or you could in general sort of have a recentering as well, so sort of theta minus z minus theta naught kind of a thing. And so you can very easily have free parameters.
So would your class of function include all possible values for this
again, so what we'll see actually is we're going to talk about this function class scriptf abstractly for most of the talk, and then you can take whichever one you're interested in to obtain complexity estimates. And whether I mean basically if you don't take a big class of free parameters, then you'll have a small function class. Sort of optimizing or estimating over it will be easier, and the bigger you make your class, the harder the optimization problem will get in this model as your function class grows. Okay, so we have this class of functions. Now, unknown to us, an oracle picks a function little f from this class, and the way we're going to think about that is again, in the simplest case, you can think of this as now nature has fixed a probability distribution inducing this expectation, right? And we of course do not know this distribution, but we would like to compute the parameter that minimizes the risk function, so the parameter that minimizes the function f picked by the oracle. The way this happens in the black box model of complexity is by algorithm making repeated queries to the oracle. So at time t, the algorithm queries oracle with a parameter theta t, and now in the stochastic, and this is actually just a stochastic first order oracle, the oracle responds with a noisy gradient of f evaluated at theta t. And again, in the statistical setting, it's very easy to obtain these noisy gradients because you can just pick a sample from the distribution that you're interested in and evaluate the sample gradient, and that's just unbiased by definition. And you can have now an algorithm basically corresponds to how it utilizes this information to compute its next query point, right? So for instance, the simplest example would be the stochastic gradient descent algorithm, which just takes a step in the negative noisy gradient direction with some appropriate step size to get the next iterate and repeats this process over and over. Okay, now in this oracle model, the way we talk about the complexity of an algorithm is by the number of queries it makes to the oracle. So we are really thinking of these noisy gradient evaluations as units of our computation and measuring the complexity in those units. And so for a fixed method m and for a fixed function f, you can ask what's the minimum number of queries needed to minimize f to precision epsilon. Right now that would be kind of unsatisfactory because that's specific to a particular method, and what we at the outset what we wanted was an algorithm independent understanding of computational complexities, and that brings us to a notion of minimax complexity, where we take the best case over all possible algorithms in this family, yes, that can interact with the stochastic first order oracle, and for each algorithm we measure its worst oracle complexity over all functions in our class script f, because we only want algorithms that work uniformly over the function class. And this best worst case complexity is referred to as the minimax complexity of the function class script f. And what we will see today are results about this minimax complexity for various choices of the function class script f.
With the class m fixed, or?
The class m is always going to be algorithms that can interact with the stochastic first order oracle. So for instance, you could then change the oracle and get a different class of algorithms, but we'll talk about just the first order oracle today. So the first class of functions that we start from is the class of convex Lipschitz functions. These are Lipschitz with respect to a particular metric. I kind of omit that for simplicity, but what you get is that the minimax complexity of optimization over this function class scales as p over epsilon squared, where p is the number of parameters and epsilon is the desired precision. Okay, so first thing to note is that we get a linear scaling with the number of parameters in this case, and
so that's kind of an answer to Christian's question. If you have lots of free parameters,
well, these are actually the statistical parameters.
These are the statistical parameters.
Yeah, these are
not from the function.
Exactly, these
not from the function class. Okay.
right. And the second thing to note is that in this case the lower bound cannot be improved any further, because in a uniform sense over this entire class of functions, stochastic gradient descent has a matching upper bound. Now one thing we often see in optimization is that the complexity estimates of functions improve in presence of certain additional structures such as non-degenerate curvature.
I mean, just to get a sense, like a priori this looks like a very, what's bad about it?
So what's bad about it, for instance, is the dependence on, you might want a smaller dimension dependence, and you actually do based on so here I make Lipschitz assumptions with respect to a certain norm. If you make Lipschitz assumptions with respect to a certain different norm, you get different dimension dependence, and correspondingly you also get a different optimal algorithm. So
you might get log p, or
you can get all the way to dimension independent actually. If you're L2 Lipschitz, then you actually get a dimension independent result, and that was actually A 1 over epsilon squared lower bound on this problem was already known since 1983 in the work of Nemirovsky and Yudin.
Wait, there's something I don't understand.
P
is the number of parameters you want to estimate.
Exactly. But it's also the number of dimensions in your optimization problem.
So for Netflix, the Netflix challenge, that's horrible.
If I have to output P parameters, how could it be better than linear in P?
So I'm not talking about the computational time that's spent inside the oracle for computing the stochastic gradient. And the time that you spend in computing the stochastic gradient is definitely always going to be, you can actually, in some cases, compute a stochastic gradient in fewer than O of P, because you can sort of compute a randomized a single coordinate gradient, and sometimes the computation of that can be independent of P even. If you just pick a coordinate uniformly at random, and just if you can compute the gradient in that direction in lesser than O of P, then even that's not necessarily true.
The cases where it's dimension independent are the cases where you could do kind of dimension reduction, pretend that you did dimension reduction.
So we'll see one concrete example of the dimension dependence being nicer in 2 slides. Yeah.
How is this a computational hardness? Isn't this a statistical hardness?
So this is, well, not quite, because so you're still measuring the number of queries you're making to the oracle to solve the optimization problem, right? So I'm not talking about the minimax error statistically. I'm just talking about the minimax complexity of solving the optimization problem to a precision epsilon here.
But isn't that the statistical problem of finding the optimal solution?
No, not necessarily, because in terms of optimization, the result applies just as well to computation of theta hat. It's not necessary that I just think it's for, right? So here we are in a completely abstract framework where we just have a function that we are trying to minimize, and we are trying to compute its minimum, and based on these noisy gradient queries, and we are talking about the number of queries we need to make to an oracle in order to minimize the function.
But obviously there could be like a much faster algorithm, but it will just have not to be in this framework that it only looks at these first order.
Precisely. Yeah, so for instance, if you can do exact gradient evaluations, you can do much faster algorithm. Statistically, or in a lot of problems that does not happen because the cost of computing a full gradient can be much more than the cost of computing a stochastic gradient.
By the way, the magnitude of the noise, does it enter anywhere?
Yes, I have suppressed that dependence for simplicity, but it's present in the results. Okay, so very briefly I want to mention that the dependence on the precision epsilon improves from 1 over epsilon squared to 1 over epsilon if you assume that the functions have a non-degenerate curvature, and that nicely matches with the known upper bounds. Again, in particular, again, stochastic gradient descent is an optimal algorithm. The thing that I want to talk about at a bit more length is an example where the dimension dependence can be much nicer. So in the statistical literature, people have talked recently a lot about what happens if you're in a high dimensional space but you have certain additional structure on your parameters. In particular, people have looked a lot at the sparsity structure. So in the same vein, we talk about the optimization of convex Lipschitz functions again, but now we assume that the optimal parameter theta star has at most s non-zero entries, and we expect s to be something significantly smaller than the total dimension. So these sorts of problems, for instance, one example where you would encounter them is if you had statistical data and you were actually trying to compute this, the sample optimum on a statistical problem that does admit a sparse solution. So for instance, if you are doing something like sparse logistic regression in high dimensions, you would actually encounter these sorts of objective functions where your theta star has only a few non-zero entries.
Wouldn't it be for your purpose enough to estimate all entries which are larger than epsilon?
Not necessarily, because suppose there are suppose your error kind, it all depends on what the sort of error metric looks like, right? So what you're saying is true if the error metric looks like an L infinity norm, but if it looks like say an L2 norm and you have a lot of entries that are below epsilon and you miss all of them, then they can add up to still something significant, right?
So this is S squared?
Yes, so it's a bit confusing because the Lipschitz assumption that needs to be made for this result is different from the Lipschitz assumption that needs to be made here, and in particular if you make the same Lipschitz assumption here, you get p squared, which is why the two results are completely consistent. It's just that in this problem you cannot make a non-trivial statement if you make the same Lipschitz assumption as before.
So do you really are you really doing any non-sparse solution, or are you keeping a bound on like the one norm of the parameters? Because you haven't kind of discussed geometric constraints on.
So because this is a lower bound, I actually assume true sparsity on the solutions. The algorithm that will match the lower bound does use a one norm constraint though.
Then that doesn't really match the lower bound, right? Because then it depends on the one norm, which is a scale.
Yeah, so the results, okay, the lower bound is assuming that you have you're sparse, but you have an L infinity on the parameter.
Right. Okay. So
and then based on that, so yeah, based on the L infinity, you can relate L1 and
right.
L0.
So this bound is really L1 norm of the parameters times that.
Yeah, kind of correct. And so yeah, the key difference here is that we get the logarithmic scaling, which is quite interesting because this is also something we do see in the corresponding statistical results for the convergence of theta hat to theta star. And in the second part of talk, I'll talk a lot more about sort of the interplay and how these two complexities might correspond to each other in a lot more scenarios. And again, the lower bound is unimprovable because there is a matching upper bound for the mirror descent algorithm in a certain geometry. I think I'm gonna skip most of the proof intuition. So the only sort of high level message that I want to convey is that even though I showed just a few examples today, the results are based on completely generic quantities that you can kind of compute for many function classes and use the framework to obtain results for many other function classes for many other structural assumptions on the parameters. And kind of all you really need to do is to sort of construct packings inside function classes which kind of represent a hard subset of functions for optimization. And the only place where sort of the key sort of new insight where this differs from what people have already been doing in statistics is the metric in which you actually construct this packing, which is something that sort of if you look at it, it ends up being very natural for optimization. I'm not going to go over what the metric is because it takes a while to describe. But once you have this packing set, you can kind of use this metric which captures a lot of properties of the function class. So things like strong convexity just naturally enter the results through the metric we use. And I did not again talk about how the geometry of the parameter set enters the results, and again that naturally enters when you try to construct packings in this metric. It just automatically shows up. But rather than stay on this any longer, I kind of want to talk about the second aspect, which tries to illustrate more of these correspondence between computational and statistical complexities. And the case we will use for this is computation of high dimensional estimators under structural assumptions. Okay, so the setup here is going to be that we have a certain parameter space. Again, as before, we are in p dimensions, but now it's a bit more statistical. So we really have a distribution we are going to think about, p theta indexed by each parameter theta, and unknown to us there is a parameter theta star, and we receive n samples drawn IID from p theta star. We would like to estimate theta star, we only have a few examples. So in the high dimensional setting, P is quite often much larger than the number of samples n. And sort of a canonical form of estimators that many people have looked at for these high dimensional problems is to try and minimize a certain loss function over the data samples subject to a constraint based on a regularizer R. Equivalently, you could of course put the regularizer up here in the objective. The two are just equivalent. So statistically, what people have shown quite remarkably in a lot of cases is that theta hat can be consistent for theta star, even when P is much larger than n, if theta star can satisfy certain structural assumptions. Computationally, of course, as we saw, there is again a similar dependence on dimension when we try to solve optimization problems such as the computation of theta hat. And what we would like to understand is, do the structural assumptions that help computational analysis also make the optimization for theta hat any easier? I'll try to answer this question by taking an example of a particular optimization algorithm and showing that this question can be answered in affirmative. And of course, since I'm choosing the optimization algorithm, I'm going to make my life easiest and choose the simplest one I can come up with, which is projected gradient descent. So this algorithm is iterative. It just takes repeated steps in the negative gradient direction with some step size. Note that this is the true gradient here. There is no noise in the gradients this time. And we are solving a constrained optimization problem, so the gradient steps can take us outside the set, in which case we just project back. Right? So this is a very classical algorithm, and its convergence is quite well understood. So in particular, if the loss function satisfies certain smoothness assumption, then it's well known that it converges at a sublinear rate like 1 on t after t iterations, which kind of looks like the blue line here. What's also known is that if the loss function satisfies an additional strong convexity assumption, then this algorithm converges very fast. So there is a contraction factor kappa such that the log of the error decays linearly, and that's why this is called linear convergence. Now, to understand the behavior of projected gradient descent on these high dimensional problems, we're going to start with a specific example of sparse linear regression. So the setup is going to be that we've got n data samples. Each sample consists of p-dimensional data vectors xi's, and the regression outputs generated according to linear model x theta star plus w. And because we are in a high dimensional regime, we need to make certain structural assumptions. So in particular, in this case, we assume that theta star has at most s non-zero entries. And in that setting, an estimator a lot of people have looked at is the so-called Lasso Estimator, where you try to minimize a least squares loss on the data samples subject to an L1 constraint on the parameter, which try.
IID here?
So the pair xi yi is an IID sequence.
It's chosen from what distribution?
Some joint distribution over xy pair for now. We're not. So just that y is generated according to this distribution. So you draw an x according to an arbitrary distribution, and then pick where w is again some zero mean noise.
Okay, so you select xi and from some distribution, wi is some independent noise, and that's how you.
Exactly. Okay. Right. Okay, so this is the problem that we want to understand, and there's been a lot of work, both statistically and computationally, on trying to understand the properties of this algorithm. In particular, there's been a lot of off-the-shelf methods that have been applied to the computational problem, as well as people have developed specialized algorithms. Unfortunately, none of the results that we know so far even explain the behavior of projected gradient descent on this very simple problem. So to explain why, let's first just see what the algorithm behaves like when applied to this problem. If we just run the algorithm on the problem for many different problem sizes, what we see are linear rates of convergence. And let me remark that this phenomenon holds not just for sparse linear regression, but for many other structured problems in high dimensions. So for instance, things like various low rank problems and so on. To see why this is not explained by the current theory, let's dig into the assumptions that theory often makes a little deeper. So often it's assumed that we have the smoothness and strong convexity assumptions for the linear convergence, and let's see these assumptions in a very simple setting where the data vectors are just drawn according to a normal distribution with covariance sigma. Okay. So what the smoothness assumption requires is that if you take the Hessian of the loss function, then its largest eigenvalue be upper bounded. Now in this case the Hessian matrix is just x transpose x over n, and standard random matrix theory tells us that the largest eigenvalue of that is at least the largest eigenvalue of sigma plus quantity p over n, and if p is much larger than n, this upper bound is going to be terrible. Okay, so we kind of don't really have smoothness effectively if p is much larger than n. What's even worse is that strong convexity assumption just does not hold. So strong convexity requires that the smallest eigenvalue of the Hessian be bounded away from 0. In this case x transpose x over n is a p by p matrix that has rank at most n. So there are at least p minus n 0 eigenvalues, and you're not going to have a non-degenerate curvature on this problem. So numerically this looks like a pretty ill-conditioned problem if we think about it from sort of the worst case scenario, and still we are getting a pretty nice convergence when we apply the algorithm to it, and we would like to explain this gap. To do that, we start from the strong convexity assumption and look a little closer at it. So what strong convexity requires is that if you look at a loss function and its first order Taylor approximation, then this gap be at least a quadratic term, and this does not happen in high dimensions. So what we do is we cut ourselves some slack. We allow a tolerance term that depends on the same regularizer R that we use to constrain our problem, and because this is now a weaker assumption, we call this restricted strong convexity. And what we are going to show is that this assumption, because it's weaker, can hold even in high dimensions. So just very quickly, what I want to say is, for instance, taking the special case of sparse linear regression, this assumption is already well known in the literature from the name of restricted eigenvalue, and people know how to prove it. So we can just piggyback on the existing literature to just get this assumption for free from the statistical papers. We also require an analogous upper bound. So the smoothness assumption that's often made requires that the loss function minus its first order Taylor approximation be at most a quadratic term, and again this does not hold with, at least with a good constant in high dimensions. So we allow ourselves some slack, again this time a positive tolerance, and since again this is weaker, we call this restricted smoothness, and again we will be able to establish this in high dimensions for many problems.
So what is the R squared here?
This is the same regularizer R that you're using to constrain the problem, exactly. Yeah. So the upshot of these assumptions is that despite being weaker, they allow us to get good convergence results. So recalling the optimization problem we have, what we can show, now we are back to the case of a general loss function. So if the loss function satisfies the RSC and RSM assumptions, then there is a contraction factor kappa such that we do converge linearly at a rate kappa, just like we were seeing. However, there is a catch. We don't converge all the way down to 0. So there is a because we are using weaker assumptions, we cannot converge all the way, and there is a minimum error epsilon squared which depends on the distance between theta hat and theta star, and we can only converge to an accuracy epsilon squared. Now from an optimization point of view, this might strike you as a very strange result, because I'm trying to solve this optimization problem and I don't quite guarantee convergence to its minimum, so what's the point? What we have to keep in mind here is that the goal here is not theta hat. We are trying to solve the underlying statistical problem, and we want to recover the parameter theta star, and there is already some distance between theta hat and theta star. Now it might be the case that theta t that you get is much farther from theta hat than theta hat is from theta star, in which case we've got a terrible estimator in our hands. It might also be the case that the theta t you have is quite close to theta hat, and in that case up to a small constant theta t is as good an estimator as theta hat is, and if we can compute theta t fast and we have a good statistical quality on it, then we are happy, right? So what we are going to try to show is that in many cases it is actually the second scenario that we find ourselves in.
Do you, when you run these simulations, do you actually see this kind of thing that you get?
If we are evil enough, yeah. So you have to work a little hard to make the problem actually sort of bottom out at epsilon squared, and you can even see it oscillate within that radius, but you have to be a little evil in the problem design. So I find that a little unrealistic, and I haven't included the results, the simulations today. Okay.
Is that occurring in a regime where your support set is much larger? Is that the?
No. So we are actually not going to make any claims about support recovery.
Right, but in the cases where you're bouncing around,
no. It's in the cases where you do not have exact sparsity. If you take an approximately sparse parameter,
right,
then you get the bouncing around.
right.
Yeah. Okay, so to see how we might have this sort of favorable scenario, let's go back first to the sparse linear regression example. We, as before, make the sparsity assumption, and for now we assume that the data is again Gaussian, although that assumption can be relaxed fairly easily. So what we can prove is that under these assumptions, RSC and RSM hold with high probability. Now this is a bit strange, because I'm going to make an assumption here that I cannot know in practice ever. This can be relaxed, it makes the presentation much harder and the proofs much harder, so I'm presenting the simpler version today. So we assume that the constraint radius rho at which we constrain the L1 norm of parameter theta is set exactly to the L1 norm of theta star for now. And if we do that, then we can show that we do have linear convergence as predicted, and the tolerance which we get has linear convergence to has the following nice form. So the first part is just the distance between theta hat and theta star, which is the statistical error on the problem, times this factor, that's S log p on n, and for statistical consistency on these problems you anyways need S log p over n to be vanishing, to be going to 0, otherwise statistically your parameter will be inconsistent. So we expect this to be a very small constant times the statistical error of the problem, which is exactly what we had claimed. And the other thing I want to point out is that the contraction factor kappa here is actually a random sample dependent quantity and typically tends to improve with sample size. So we can verify this in simulations. If we run the problem on a fixed number of parameters for varying number of samples, initially we do not see RSC and RSM assumptions being satisfied, and the algorithm actually oscillates. But as we increase the number of samples further, we start to see convergence, and the convergence accelerates as the number of samples is increased further because the contraction factor improves. Sorry?
So this improvement is due to that kappa. Kappa.
And we will see a more quantitative demonstration of that in 2 slides.
This is natural log, or like see, it's exactly when 1 log when S log p is 1 is exactly doesn't work, and 1.2.
Yes. I don't remember the base. I believe it must be natural log, but I mean even the statistical theory requires this to be at least like twice S log p or something.
So you seem to be better because already in 1.20.
No, 1.25 is still oscillating. Yeah. So in 5 is the first time we start to. Okay. A lot of people will be angry with me breaking statistical lower bounds if I claimed such things. Okay, now similarly you could, instead of varying the number of samples, you could fix the number of samples and vary the number of parameters, and again we see as the number of parameters is increased from 5,000 to 20,000, the convergence slows down because the contraction factor worsens. Now one interesting part is that we can actually capture the rate at which the slowdown of the contraction factor happens quantitatively, and what the theory predicts is that instead of holding the number of samples fixed, if you rescale them appropriately with the number of parameters, then this slowdown should not happen and the contraction factor should stay constant. So indeed if we do the rescaling, we see that the 3 curves exactly line up on top of each other, meaning that the particular quantitative prediction is sharp. Another problem that falls within the purview of this theory is the low rank matrix completion problem, and the way we formulate it is that we think of our observations as randomly picked entries of a matrix theta star corrupted with some zero mean noise, and we make the structural assumption that theta star has rank at most r, and in this case an estimator that a lot of people have looked at is to minimize the least squares error on the observed entries of the matrix subject to a constraint on the nuclear norm, which is just the sum of singular values of the matrix. And what this does is it tries to enforce sparsity on the vector of singular values. So it gives you a low rank matrix because a small number of non-zero singular values gives you low rank, right?
So why is what you're going to get here going to satisfy that that condition of yours? I mean,
yes. So that remains to be proved, and we proved that.
I see.
Yes.
Okay.
So it can take substantial amount of work to establish the RSC and RSM assumptions. They're not always straightforward to establish, and in this case actually it does take some work to establish them. And again, if we set the constraint radius very favorably for now, then what we get is that we have linear convergence to an error that's again related to the distance between theta hat and theta star for this problem.
Shouldn't this error be multiplied by
Not in this case, not in this case. So this problem has a very tricky structure on the RSC and RSM that's a bit different from the sparse linear regression problem, and you actually do not get the times. So this is exactly sort of the minimax distance, or not minimax, the distance we know between this theta hat and theta star. There is an extra log p compared to the minimax rate for this problem, but this theta hat minus theta star is exactly on this order. So in this case you can lose constant factors, but up to a constant factor you still have the right answer. Again, we can verify this in simulations, and initially we see no convergence, starts to converge, and convergence accelerates as the contraction factor improves.
Theta hat actually equals theta star. That
Yeah. So
You still have an additive.
yeah, so we are not guaranteeing exact recovery.
And is that what the optimization problem guarantees as well? Is this the computational issue or is this a statistical issue?
Actually, okay, so it is possible actually that in the case where theta hat is exactly equal to theta star, you might be able to improve the result, because typically, so at least the cases where we kind of know how to prove theta hat is equal to theta star often requires some sort of incoherence on theta star, and it's quite likely that if we assume incoherence, our RSC and RSM assumptions will improve, and we might get a better scaling here. We might get the same sort of theta hat minus theta star term entering in here that we had for sparse linear regression. So yeah, that's actually a good point, but I haven't checked what we get for incoherence. This is without incoherence. This just assumes an L infinity bound on theta star.
And for the regression case, that was without.
That was just without any assumptions. So you just require theta star is S sparse, and you basically require sort of you essentially require X to have some sort of a sub-Gaussian design.
Okay.
Right. Okay. So again, these are just a couple of examples. The results extend to arbitrary regularizers from a certain family and apply to many other problems, in particular, for instance, group sparsity which is of interest for solving multitask learning problems. They apply to other loss functions. So for instance, you can show these assumptions for generalized linear models, although again the technical aspects are a little more involved there. And finally, even though everything I showed today was where you have a loss function with a regularizer based constraint, the results also apply to the form where you have a loss function plus regularizer, and in that formulation has the nice aspect that you do not need to know these quantities such as L1 norm of theta star or nuclear norm of theta star for that particular formulation. So So actually setting the parameters in that formulation is easier, and so quite naturally the proofs get harder. I was gonna mention something about distributed stuff, but I think in the interest of time I'm gonna just skip right to the conclusion, and I'd be happy to talk more about it offline. So
can you just say maybe
Yeah,
the bottom
maybe
there,
the
what's the
2
result?
Okay.
3 minutes on it.
Sure. So kind of the basic picture we're gonna have, we sort of carry for the distributed framework in our heads often is that we've got a big data set. We split up the data set into smaller chunks, giving each computer in our network a chunk of the data. So based on that, each computer can define its local loss function based on just computing the sample loss over its subsample, and then minimizing the entire loss over the data set kind of corresponds to just minimizing the sum or the average of these local functions. And you want a distributed algorithm to minimize this. So in particular, what I mean by a distributed algorithm is if you're given a sort of communication topology underlying this network, then you want an algorithm that respects the topology, only communicating along the edges in this graph. Right, so these are kind of like the message passing algorithms that people have seen a lot.
Do people usually run these things in clusters that are not cliques or something?
So so in a cluster you basically have it's not exactly a clique. It's more often like a sort of hierarchy, because you're okay with everything within the same rack talking to each other, but then you want to minimize the across rack communication and so on. So there are certain constraints that are definitely present. And there's been a lot of work so this particular form has been kind of one of the canonical forms of distributed optimization problem that people in controls and distributed algorithms literature have looked at for many years, and there's been a lot of work. What we did was, so we also proposed a new algorithm to solve this problem, but the emphasis in our work was to understand how the structure of the network interacts with the convergence of the algorithm. And so we characterized the convergence dependence on the structure and showed kind of things that you expect to see, that a complete graph topology is the best topology, and expanders are almost just as good, and if you go to the chain graph, that's going to be the worst. Unfortunately, most of the results that were present before were kind of the worst case results that you get for chain graphs. So kind of having a topology based convergence rate was one of the key contributions in this work, and we showed robustness to certain things like stochastic communication. So if you've got link failures, or if you just want to randomize the communication to save on communication, then you can do that. We showed robustness to stochastic gradients. So again, you don't need to run the underlying algorithm with exact gradient evaluations. But what was unsatisfactory about this and a lot of the past work was that typically we observed loss in convergence rates due to decentralization. So because we are trying to solve this problem in a decentralized way, where the functions FIs are not known centrally, but known split over a network, we were kind of seeing that having a complete graph where everything is present in the same place is the best thing. And while that makes sense in a completely arbitrary case where these local functions FIs are arbitrarily different, it does not necessarily make a lot of sense in the statistical case, because these functions share a lot of structure. They are based on IID data from the same distribution quite often, and we gotta be able to exploit their dependencies somehow. And so Ohad here, along with Lin Zhao, Ofer Deckel, and Rani Gilad Bakrak, had some very nice work on showing that you can actually, if you run a more synchronous algorithm, then so the algorithm that you get in the most general setting, they can often be very asynchronous. If we run a slightly more synchronous algorithm compared to them, then they showed that you can actually get up to linear speedups as a function of the number of nodes, instead of having a slowdown due to having the problem split over a network. And we have sort of further built upon that, and sort of we have an algorithm that's slightly more asynchronous, but still less asynchronous compared to the arbitrary case, which still preserves these linear speedups, at least asymptotically. So kind of again here the key message that I want to convey is that this is a very well researched problem in distributed algorithms, but because people were looking at very general structures, if you further exploit the statistical dependencies in the problem, you can actually get a much better result than that is possible in the worst case. Okay, and by extending these ideas and combining lots of other tricks and techniques, we were actually able to solve the sort of click prediction problem over a big data set that I mentioned early on, over a network of 1,000 nodes, training in a matter of something close to an hour. Okay, so I hope, wrapping up, the message I managed to convey a bit is that in many modern statistical problems, data is not the only bottleneck. Computation can be an equally important bottleneck, and what's very fruitful for many of these problems is to try and attempt a joint analysis of their statistical and computational complexities rather than trying to understand them individually. And this is a challenging problem in general, so we looked at various different ways of posing the general problem, and saw some results about fundamental computational complexity of certain estimation problems, about how one can leverage statistical structure to for better analysis of algorithms, and how we can get better distributed algorithms for statistical learning problems, very briefly. Now this is just a brief, very brief survey, so there's lots of more directions for future work and lots of other ways of looking at these problems. So for instance, I talked about one particular Oracle model of computation today. There are many other Oracle models, and in particular the one I described today captures certain computational aspects of the algorithm and ignores certain other computational aspects. So getting more and more realistic oracles would be very interesting for getting more and more realistic complexity results in the Oracle models. Getting more better asynchronous algorithms for distributed settings that can still preserve speedups, again, I think is going to be very important, because you can't really afford to always run a very synchronous algorithm in a distributed setting. And one thing that I did not talk about today but is of a lot of interest to me and that I've worked on is, again, oftentimes you just want to impose a hard computational constraint on your algorithm and demand that it do something reasonable within that constraint, rather than kind of just potentially giving up and not doing anything. And in particular, we want some understanding of what can be optimal algorithms statistically under various computational budget constraints when imposed in a hard manner. And this is again something I've looked at for at least one scenario of model selection, and extending these to other statistical settings is again of great interest to me and to community as a general, I think. So that's all, and thanks a lot for your attention.
So in your rates in the first part of the talk, these minimax rates, you kind of ignored the geometric, at least in the statements of theorems, you ignored the geometric parameters, because really what you have is unbounded parameter space.
So you can assume that the parameter set, for instance, what we assume contains an L infinity ball of radius r, and then the radius of the L infinity ball enters the results. And for instance, so you can see, and so for instance, if you take an L infinity ball, of course, then it's just a unit ball of L infinity, then this is just 1. But for instance, if you take a unit ball in the L2 norm, then this becomes like 1 on root d and 1 on root p. So you kind of get the dimension, you lose the dimension factor over the L2 ball, and so on.
So you have the ball it contains as a function of the norm, because this is the infinity ball.
No, unfortunately, the way our constructions work right now are they kind of start from doing a construction exactly over the L infinity ball always. So that is I have ideas for kind of making all that cleaner, and also Sasha has a paper where he's also tried to do similar things, but again they yeah, so there is hope, and there are ways I think to get around this, but for now it's all sort of L infinity centric.
It's still open, like if mirror descent is kind of an algorithm which takes into account the geometry of the problem, and this doesn't show that that algorithm is tight for like.
Well, so actually there is the recent result of Karthik, which I think. So in the online setting, Karthik had a paper at NIPS which shows, sort of his paper was called On the Universality of Mirror Descent, which was trying to show by arguing about the value of a game. But and Karthik was telling me that he has a stochastic result, but it's not available yet. So I don't know, that might already be addressed now. Yeah. Yeah.
You mentioned the sort of Netflix or sort of matrix completion problem. So that might be a little harder to parallelize, right, or not?
Yeah, so unfortunately at least the existing theory does not give a direct way of parallelizing it, although I think some of the more recent work that's kind of close to completion that we have might help develop parallel algorithms for that as well. But yeah, we don't have anything at the moment, at least. I mean, one thing is that a key bottleneck in sort of the Netflix problem is that in order to, at least the kinds of algorithms I talked about today, you have to sort of do SVDs over a big matrix. So if you could just consider parallelizing the SVD part, and that's something that numerical linear algebra people have looked into, and that would already be a substantial help if you can parallelize the SVD part for the problem. But it's again in practice you don't need to do a full SVD because these are low rank matrices. There's lots of sort of approximate SVD tricks that people do use. So yeah, it's kind of still open how to properly parallelize the problem, I think.
So also the practice in theory is sort of far away than there, upon lower bounds in practice or not?
Sorry?
So how do your bounds apply to that problem?
Which bounds?
Well, he said he doesn't have them yet, right?
No, but if you don't, okay, so then give up on the parallelization. So what's your general setup? Can I apply it to this matrix completion problem? Or?
No,
no, not this distributed setup right now does not apply.
Oh, he just wants to know how well your non-distributed results on the Netflix problem are relative to other best known.
Oh, I see. So as far as I know, okay, so under certain conditions, people have studied actually computationally much simpler techniques based on just sort of doing sometimes even doing a single thresholding of the singular value vector can work, but that requires again stronger conditions. Under these conditions, I do not think that there was linear convergence known for any matrix completion algorithm to the best of my knowledge. I think what people were using mostly was this sort of augmented Lagrangian or Nesterov style algorithms, which all I mean the assumptions that went into them were sometimes very similar to the RSC and RSM assumptions, but often those assumptions were kind of just made without proof. And part of the work that we did was to make sure that we have all the conditions we need proved concretely. So I think, and this really I think is kind of the best possible we can hope to get. I mean, we can hope to maybe improve this part a little, but this part kind of is the best possible we can hope to get, I think, because even if you had true smoothness and strong convexity, you cannot do better than linear convergence. So
But you hope the second term under RIP would be
yes. Well, okay, for matrix completion you can never have RIP. You can have
RIP, but
under incoherence I hope it will improve.
Because it's basically what you have in the first one. You have the
Right,
Gaussian design
right,
is basically
right,
RIP.
right. Well, no, I mean, you can have very correlated designs. You can have basically toplets designs that would grossly violate RIP, and that still you can get. I mean, we actually do simulations on that.
Maybe we should, because there
Yeah.
are some people.
Of course. Yeah.
Thank you very much.